There's a group of people some years back called the High Z Supernova Search Team, among them Saul Perlmutter, who got the Nobel Prize in Physics for making some discovery that the universe was accelerating. I've got one source here, named Adam Dempsey apparently, that claims to have real data from a group led by the Nobel Prize winner, Adam Rice, who happened to be on that High Z Supernova team. In this file, sndata.txt, he has listed 206 of these supernova according to their distances in redshifts. He lists redshifts from 0.01 all the way to 1.2 and distances of up to almost 8,800 megaparsecs, which is about 30 billion light years. To get that, you would take 8590 times 3.26 light years per parsec, and then divided by 1,000 because we're converting from millions to billions, and you get 28 billion light years. Now the problem with Adam Dempsey's presentation here is that he just gives the distance, but he doesn't tell how it lists distances without any explanation of how they got it from the actual data. It doesn't give any reference to the documentation from which he got these numbers. And 3, he does not give any information of the direction to these supernova in space, that is, the right ascension and declination. What I'm looking for is a table of data regarding these supernovae that reports distance, redshift, right ascension, and declination for each of the supernova. If I could, I would like to see for each data point a note on precisely how they calculated the distance based on the apparent magnitude, and precisely how they calculated the redshift based on molecular and atomic absorption lines. I do see that the High Z Supernova Search Team does have a list of publications. Here there are links to 8 papers and 2 papers without links. And then there are 12 conferences listed, 8 of which appear to have links and 4 that don't. And then it has this thing that says IAUC Circulars. However, when I click on that link, it just seems to go nowhere. That being said, I am able to go out and Google IAU Circulars myself. And if we come down here and click on Supernovae List, now we click on All Supernovae, we see that there's a fairly vast array of supernova data, all the way from 1054 AD, actually 1006, all the way up to 2016. Yes, 2015. In every one of these data entry, you can see right ascension, declination, type, right ascension, declination, type, and magnitude. But if you want redshift, you're going to have to go somewhere else. Now, some of these have more detail listed in documents called CBETs. Others have more detail listed in IAUCs. Now what I've done is gone down the list looking for data in particular from the High Z Supernova Search Team. We'll just come over here and right click, open link in a new tab, and then you have to scroll down a long ways before you see it, but here's one of their sets of data, and you can see in this set of data they tell us the type 1a and the Z value, and they've got all the way out to 0.83 in this set. So I went down the whole list and copied each data set from the IAU circulars from the High Z search team for type 1a supernovae. The data I pulled included the name of the supernova, the date it was found, the right ascension, declination, magnitude, and of course magnitude redshift, and of course type. I also had this detail R or I, and I think that has something to do with the filter used to discover the magnitude. I used a formula to figure out from the magnitude what the distance is. The idea is that if a type 1a supernova went off 10 parsecs away, it would show up as a negative 19.3 magnitude object. That's about 1,000 times less bright than the sun is in its current position. So assuming it would be negative 19.3 at 10 parsecs, we can calculate how far it is by comparing its apparent brightness, little m, to its actual brightness, big M. And this formula here gives us exactly that distance. Then we can calculate its distance in light years by multiplying the number of parsecs by 3.26, and its distance in gigalight years by dividing by 1,000,000,000. Now the next formula here is the big difference between my hypothesis, the hypothesis that I want to propose, and the current standard cosmology. My proposal is that we live in a Minkowski spacetime where the velocities of objects is exactly what one would expect from the relativistic Doppler shift equation. And this is basically the relativistic Doppler shift equation. So if you look up redshift on Wikipedia, you'll find several redshift types based on different geometries. My calculation of velocity is based on this equation here, relating redshift to motion completely in the radial direction. Let me go back to Adam Dempsey's data for a moment. Recall that his website reported, all his website reported was redshift and distance. So you can't get any sense of direction. I noticed that his furthest supernova is not at 28 billion light years, but actually at 11,749 megaparsecs is almost 40 billion light years. So I made a graph of this data in a completely different way than you usually see it. The horizontal coordinate here is distance, and the vertical coordinate is time. The end of each of these lines down along here represents a supernova event. This supernova event here, for instance, happened 20 billion years ago at 20 billion light years distance. All of the supernova events that we see happened at a time in the past in billions of years equal to their distance in billions of light years. Hence, I'm not plotting the location of the supernova along the line t equals 0, but instead along the line t equals negative d. Now, I'm making a rather bold assumption that these supernovae, before they were type 1a supernova, they were carbon core white dwarfs. And before they were carbon core white dwarfs, they were red giants. And before they were red giants, they were main sequence stars. And before they were main sequence stars, they were clouds coalescing out of the interstellar gas and dust. And this interstellar gas and dust had roughly the same velocity on average as the white dwarf that just went supernova. So if we assume that the constituent particles of the supernova had, on average, the same velocity as the current exploding supernova, then these are the world lines of that coalescing cloud of dust from whence the supernova was born. And you can see that the trajectories here don't all meet back at a point in space and time, but rather it's as though they all came from a point in space, all at different times. Now, eventually, I would like to get directional data for all 206 of the data points in Adam Dempsey's file, but for now I'm working with 53 supernovae that I found in the IAU circulars. Now, there's some work to be done with this data. For instance, to convert from right ascension in hours, minutes, and seconds to degrees longitude, you have to take hours plus minutes over 60 plus seconds over 3600. Furthermore, you have to multiply by 15 degrees in an hour and pi over 180 radians per degree. Then, if you want to get your declination into an angle from the North Pole, once again you need to take degrees equals minutes over 60 plus seconds over 3600. Then take 90 minus the degrees north of the equator to get degrees south of the North Pole. Once you have r, theta, and phi defined in this fashion, then you can find the Cartesian coordinates from z equals r cosine theta, x equals r sine theta cosine phi, and y equals r sine theta sine phi. I'm trying to decide whether to fix this issue while I'm making this video. Currently there's an error here because I'm calling this current distance from origin, and it should be observed distance from origin. To know where the supernova material actually is now, we would have to add its current velocity times time, the observation delay time, t equals d over c. So I'm going to add this function, predicted current distance from origin, which is just 1 plus v over c times the observed distance from origin. Now we've got an animation we can work with. The animation starts at 70 billion years ago and then slowly progresses. Material doesn't come out of the center all at once, but 2 or 3 pop out here and then more and more. At a little less than 54 billion years ago, you start to see the first trajectories. There comes a couple, and I'll just let that run. Now, you might think this seems impossible because we want just one Big Bang event. You don't want kind of a stream of particles popping out from the center. But I've got reason to think that this could be a possible way of imagining it, even though you wouldn't expect it at first glance. And it has to do with time dilation that, well, I'll show you a space-time diagram for it later. But the time dilation has to do with all of the particles in the center moving back and forth at nearly the speed of light. Okay, as they get out towards the edge of these points, this is the point where the supernova actually happened, that we actually observed. And these particles are continuing outward until we get to the present day, until time equals 0, because the actual endpoints of those lines, and I'll speed up the animation so you can see it happening a bit faster. But the basic idea is that it starts out at the center, and it doesn't necessarily have to all come from this exact same moment, because you could imagine this being very dense down here, and so think particles are constrained by pressure, volume, temperature, and then as the universe expands, then finally the particles can be released from that region and have the opportunity to move out. Now there's one last thing I want to talk about here, is this idea of an empty universe. This is a reference to a Milne model, where the Milne model was a special relativistic cosmological model proposed by Edward Arthur Milne in 1935. It is mathematically equivalent to a special case of the FLRW model in the limit of zero energy density, in other words, an empty universe. What I realized I needed to do is essentially embrace the fact that, in the sense that they are defining empty universe, this model that I'm describing is an empty universe, or more to the point, approximately empty. This F here stands for Friedmann. And Friedmann is associated with the Friedmann equations. And the Friedmann equations the first Friedmann equation looks kind of like this. Now, if lambda and k were 0 here, it would just be the escape velocity equation from a sphere of constant density surrounded by a vacuum. So to show that, I'm going to use kinetic energy of each particle in the system is equal to the gravitational potential energy of each particle in the system. So here's the basic escape velocity equation, that the kinetic energy, 1/2 mv squared, is equal to the gravitational potential energy, gm, m, and this should just be an r, not an r squared. So we're only concerned about the mass of the sphere inside the radius that we're at from it. And this is a big leap right here, because suddenly we've gone from no assumption about the universe to assuming that it has a spherical, well, we've made two assumptions. The first ridiculous assumption is that the kinetic energy of each particle is equal to the gravitational potential energy, and that is by no means anything that we should be taking a priori. The second crazy assumption that is made in the Friedmann equation is that the universe is basically a uniform density sphere, which there's not really any particular reason to accept that, but that is, I guess, part of the cosmological principle that we're applying. But more to the point, outside that sphere, they're assuming it's a vacuum, that there's nothing outside of that uniform density, that it's uniform out to a certain radius, and then it goes to 0, because that's what I'm going to be using to solve this, that the volume of that sphere is 4/3 pi r cubed, and we can cancel out the masses, and then we're assuming that the velocity of every particle in the universe is going at its own escape velocity. So this v is the change in x over change in time, or the change in radius, r dot over r. That's the dr dt. And so then this r squared and this r cancel out, and that's left us with a simplified form of the Friedmann equation. So what am I doing for this? What other assumptions am I making? For one, I'm not making this assumption. Well, I'm not going to make either of these assumptions. I'm not going to assume that the velocity of the particle is equal to the escape velocity, and I'm not going to assume that the universe is a constant density sphere surrounded by a vacuum. But we do have all the particles are accelerating towards some center of mass. And I would agree that this statement would be true. All of the particles are accelerating towards some center of mass. But the idea that that it's going to be obvious where that center of mass is. So my guess is that the universe is probably more like a hollow sphere with nearly infinite density around the outside surface, that the matter is concentrated out past the cosmic microwave background surface. If this sphere has a center of mass, it is currently over 40 billion light years from us, and there's likely almost an equal amount of matter 40 billion light years in the other direction. So for everything we can see in the visible universe, there is little, let's say little or no, detectable tendency for anything to accelerate one way or another due to the large-scale matter distribution of the universe. Another idea is that the universe is older than the particles within it. Basically, that's to say the particles were not free to spread out for the first period of time. They bounced back and forth within a limited region for a very long time, and then finally the universe was spread out enough that you could see particles getting away out of that center. And so when those particles are moving back and forth and back and forth and back and forth at nearly the speed of light, they essentially don't age. The twin paradox provides a mechanism by which a twin traveling back and forth can essentially not age while the universe around him expands at the speed of light. The thermally The thermally accelerated particles of the early universe see it as inflation, where the universe expands faster than the speed of light. But to put that in other words, more distant particles left the primordial universe earlier. The distant particles left, and then more nearby ones, consecutively more nearby particles left. Well, this Thanksgiving, I am thankful that I had time to look up some real data and do some serious modeling with the Mathematica software. So I'm going to post this video on YouTube, so please like, share, comment, share, or however YouTube works.